Greetings, travelers. My name is Ruofei Du. I'm a research scientist at Google. Today, I'm going to present our open-source magic, DepthLab, real-time 3D interaction with depth maps for mobile augmented reality. Augmented reality has gained mainstream popularity on mobile devices with thousands of AR apps, such as Pokemon Go, Snapchat, and IKEA Place. These apps are typically supported by Google's AR Core or Apple's AR Kit to place virtual objects anchored on flat, physical surfaces, or to invoke an experience as a reaction to detected AR markers. However, is direct placement and rendering of 3D objects sufficient for realistic AR experiences? Not always. For instance, without awareness of occlusion, virtual content looks like it's pasted on a screen rather than in the real world. With depth map and occlusion-aware rendering, the virtual cat in augmented reality looks much more realistic than the former one. Here, correct occlusion helps ground content in reality and makes virtual objects feel as if they are actually in your space. Next, we wonder, how can we bring these advanced features to mobile AR experiences? With Google's AR Core Depth API available on millions of Android devices, we wonder, is there more to realism than occlusion? What about surface interaction, realistic physics, and path planning? We are used to these concepts in typical 3D games. Why not in AR on our phones as well? Next, please enjoy.
DepthLab encapsulates a variety of depth-based UI or UX paradigms, including geometry-aware rendering, real-time visual effects such as rain, snow, flooding, and relighting, and surface interaction behaviors such as surface splatting, real-time mesh generation, and physics simulation.
DepthLab is available on a large number of Android devices with a single RGB camera. We compute live depth map by the depth from motion algorithm introduced in SIGGRAPH Asia 2018. Instead of learning depth from a stereo pair of camera, we use depth from motion, providing stereo images across time as the phone moves through the environment. However, this presents additional challenges compared with traditional stereo. While traditional stereo has full control of how the cameras are arranged with a wide camera baseline, stereo from motion cannot control how the user moves the camera, although cannot guarantee field of view overlap, velocity match, motion blur, autofocus, and etc. Users likely to move very little. They want to arbitrarily move the mobile phone. So the important considerations include which keyframe to choose and how to maximize information generated from each frame. Keyframes are chosen from a pool to give the best keyframe to give the best possible depth for the current frame. Oftentimes, the keyframe is just a few centimeters away from the current frame. Then we use stereo matching algorithm, providing a sparse and noisy depth representation that needs to be filtered, interpolated, and smoothed. We call it raw depth in the upcoming AR Core. The depth image is matched for every camera image processed by AR Core at 30 Hz. An application can acquire the latest depth image for the current frame. For more details, please check out our SIGGRAPH Asia 2018 paper, Depth from Motion for Smartphone AR. Currently, our depth 16 image format allows for depth sensing up to 8 meters, and the best depth measurements are between 0.5 meters to 5 meters. However, even with real-time depth map, there's still a large gap between the raw depth data and the typical expertise of mobile application developers who are not experienced in handling depth data. So in DepthLab, we process the raw depth map from AR Core Depth API and provide customizable and self-contained components for mobile AR developers to build more photorealistic and interactive AR applications. To explore the design space, we conducted 3 brainstorming sessions with a total of 18 participants and proposed a total of 39 aggregated ideas. These participants include researchers, engineers, and UX designers who have worked on AR or VR-related projects. We listed these ideas in the supplementary material. Please feel free to scan the QR code. We will also show the QR code in the end. When developing DepthLab, we architect and implement a set of data structures and real-time algorithms for mobile AR developers. We generated 3 kinds of data structures: depth array, depth mesh, and depth texture. Depth array stores depth in a 2D array of 16-bit integers on the CPU, which is typically 160 by 120 pixels and above. Second, depth mesh is a real-time triangulated mesh generated directly from the depth map. We'll introduce later how we generated the depth mesh. Third, depth texture, which is basically a GPU texture decoded from the depth array and interpolated to larger resolution. Based on the data structures, we classify our DepthLab components into 3 categories: localized depth, surface depth, and dense depth. Localized depth uses the depth array to operate on a small number of points directly on the CPU. For example, by converting between the screen space with the world space, DepthLab provides a 3D-oriented cursor. The cursor orients according to the normal vector of the physical surface and details about its distance to the ground and to the camera. Computing usable normal maps out of low resolution and coarse depth maps can be very challenging. A simple cross product may yield noisy or invalid results due to depth discontinuities, holes, and outliers in the estimated scene. In DepthLab, we provide 2 real-time API to compute a more stable depth normal map in real time on both CPU and GPU. The basic idea is just to simple 2-ring or even 4-ring neighborhood to get a smooth normal map. Here is the comparison before and after we do the averaging on the normal map. Our algorithm can effectively smooth the normal map while keeping a reasonable accuracy for developers. And in DepthLab, we provide a library to cast and reflect virtual laser array to leverage the smoothed normal map. With localized depth, we can automatically plan a 3D path for the avatar that avoids occlusion, that can avoid a collision with the statue by making the avatar hover over the obstacle statue. Particle effects can also be achieved through depth map. For example, each raindrop tests for heat with the physical environment and renders a ripple upon a collision. In our work, we forego surface reconstruction and directly represent environmental depth measurements as meshes. This technique relies on a densely tessellated chord in which each vertex is displaced based on the projected depth value. After initializing the depth, no additional data transfer between CPU and GPU is required during the render time, making this method very efficient. With surface depth, we implemented physical collider. Note that the creation of a mesh collider happens at a lower resolution on the CPU in runtime. However, we only perform the mesh collider generation each time when the user throws a new dynamic object into the AR scene, instead of running it at every frame. This operation is computationally expensive and not continuously needed, as the physical environment is mostly static when you are throwing the objects. An advanced example is color balloons thrown onto the physical surfaces with texture decals. The balloons will explode and wrap around surfaces upon contact with any physical object, such as the corner of a table. 3D photo effect is also included in DepthLab with texture projection mapping techniques. When the user clicks the 3D photo capture button, we save the current camera image, depth image, and camera parameters. Given the screen center, we first resolve the central vertex in the real world based on the current depth map. Next, we generate a frozen depth mesh. Based on the camera's world position, we can compute the directional vector from the camera to the central point of the screen. Next, with a cross product, we can compute the plane perpendicular to the directional vector. Finally, we rotate the camera and recompute the projection matrix based on the camera's position and project the cache texture to the depth mesh directly. And you can see the reprojected texture looks like a 3D stereo image effect. As for dense depth, we introduce a built-in depth-guided anti-aliasing algorithm to reduce the artifacts due to the low-resolution depth map. The motivation is that closer depth pixels are typically larger, so with simple neighboring pixels, when sampling neighboring pixels, we use a larger kernel size for pixels with smaller depth values. Due to the compute constraints on mobile AR, we recommend interactions with dense depths to be implemented fully on the GPU with compute or fragment shaders. As for real-time relighting, methods based on BRDF such as phone or Lambertian models usually require a normal map, which can contain artifacts around object boundaries in low texture regions. In our approach, we compute the photo intensity at the points when the rays intersect with physical surfaces. Please refer to the paper for more detail. Imagine a ray casting from the light source to the target pixel. The intensity of the photon will decay when traveling along the ray. The intensity is greatly reduced when it hits an obstacle, and the pixel should look much darker with more obstacles along the ray. With a little scattering, we can achieve more interesting effects such as relighting with sunbeams. Here is a sun. DepthLab also enables wide aperture effect, which can be focused on a world-anchored point. Unlike traditional photography software, which only anchors the focal plane to a screen point, DepthLab allows users to anchor the focal plane to a physical object and keep the object in focus even when the viewpoint changes. For example, just one tap on the flower, it will automatically keep in focus no matter the user approaches close or approaches far. Of course, dense depth components also included occlusion-aware rendering, as we introduced earlier, and fog effects. Next, we build a minimum viable application to profile a typical usage of DepthLab. To evaluate the performance of key DepthLab components, we made the application with a point depth example, which is the oriented reticle, a surface depth example, which is a depth mesh generation, and a per pixel depth example, which is a visualization of depth map. We ran our experiments in 5 locations, each running 5 minutes, and our simple application runs at over 100 frames per second, while surface depth is the most time-consuming part. In the second test, we evaluated the performance of the real-time relighting, one of our most computational expensive technique. According to the results, we recommend 4 to 8 samples per ray to deploy our relighting model on Pixel 3 or comparable mobile devices. In the third test, we evaluated the performance of the wide aperture effect and recommend a kernel size of 11 to 21 for real-time performance. We shared DepthLab with both internal and external partners. For example, DepthLab components are used in Snapchat, Line of Play game, in the Mirror app, TeamViewer, ThinkViewer, and more. As for limitation, DepthLab is designed to enable geometry-aware AR experiences on phones with and without time-of-flight sensors. However, we have not yet explored more in the design space of dynamic depths. In future, we envision live depth to be available on many IoT devices, with camera or depth sensors in the future. Each pixel in the depth map could be associated with a semantic label and help computers better understand the world around us and make the world more accessible for us. Finally, we open sourced the DepthLab library on GitHub to facilitate future research and development in depth-aware mobile AR experiences. We believe that this library will allow researchers, developers, and practitioners to leverage the base interaction to build novel, realistic AR experiences on regular smartphones. Finally, I would like to thank all my collaborators, including Eric, Max, Luca, Evo, Jason, Joe, Joes, Josh, Nuno, Sharam, Adash, Kong, and David for their hard work behind the scenes. And thank you everyone today for listening to my talk. Any questions are welcome. Thank you.